starting early.
Okay.
You get to 9 because, yeah, you get to 9.
Okay, get 4 bonus. Beware. All right, so let me remind you of what we did last time. So M as a smooth manifold. And the de Rham complex of M, so these are the complex valued forms. This is the C valued forms, differential forms. So that's a complex. And its cohomology means kernel of exterior derivative mod image of exterior derivative is the de Rham cohomology. And that's by the classical de Rham theorem, that's the usual cohomology. We're trying to generalize this to the fundamental group. So we defined iterated integrals, which are functions on the path space of M into C. They can also have other values. If you take the forms to have values in some other associative algebra like matrices, the value of this function will be into matrices. But anyway, so what does this do? It takes a path to the integral gamma over W1 WR. When R is equal to 1, this is the classical line integral. I should say here Wj, each of these is a 1 form on M. And what is this? This is just a so-called time-ordered integral. I didn't mention, but that's a term physicists use when they do compute Feynman diagrams, apparently. Oops, TR. And so these things have all sorts of wonderful properties. I should say here gamma star omega j is equal to fj t dt. So there are different variables in these things, but basically you integrate the first guy, multiply it by the second, integrate that, multiply the result by the third, integrate that, and so on. And the paths here are piecewise smooth. So we can integrate. And then general iterated integrals are linear combinations of these with the constant function. So they form a whole bunch of stuff, which I'll call px, say y, of m, is going to be the set of iterated integrals, so linear combinations of integrals w1, wr, but you restrict them to pxy of m. Pxy stands for the paths that start at x, end at y. And something I didn't introduce last time because I had my time taken away from me is that iterated integrals are filtered by length. So let's talk about the length filtration. So LR of, say, this is just the span of, I should also say you have a constant here. So this is, say, R greater than or equal to 1. I often think of 1 as being the iterated integral of length 0. That's a very good convention. Just the constant function 1. But anyway, this is the span of 1. Well, it's the span of the integral W1 WR, n, where n is equal to or less than R. This is a well-defined filtration. If you can rewrite these, you can only ever make them shorter. You can never, well, all right. And so let's now take x equals y. Just look at the loop space. There are analogous statements for path spaces from x to y. And we have properties. So we have, the important properties are, first of all, the augmentation. So I'm gearing up to state a more detailed version of the de Rham theorem. The augmentation is just, you just take the constant term here, right? So it's going to be the sum, well, C plus the sum of the integral W1 WR just simply goes to C. You can think of that as evaluation at the constant loop at the base point. So it's really a evaluation at what I'm going to denote by 1x, which is the constant loop at x. You just stay at x, never leave home. 2 is the product. So this is given by the shuffle product formula. Goes to the sum over all shuffles of type RS, W sigma 1. So we discussed this in detail last time. And this is dual, this is just corresponds to pointwise multiplication of functions. So this is dual to gamma goes to gamma comma gamma. The diagonal map, right? So multiplication of functions is dual to the diagonal map. And we've got the coproduct, which is integral W1, WR goes to the sum J equals 0 to R and here the convention is that if J is equal to 0, this is just 1. Right, so this is dual to, what's it dual to? Multiplication of paths. Right, so this is just the formula. It says if you integrate this on alpha beta, it's the sum of this evaluated on it, alpha times that integrated on beta. And there's the antipode, which is just integral W1, WR goes to minus 1 to the R, integral WR, W1, and this is dual to gamma goes to gamma inverse. Right? So I'm writing this down so that everything looks like something that you would see in the theory of algebraic groups. And indeed, iterated integrals are functions on not an algebraic group, but there are functions on a pro-algebraic group. And I'm not going to go in that direction because it requires too much footwork, but I'll make a remark. All right, so what we have is that, and there's also nilpotence. Which says that integral W1, WR evaluated on alpha 1 minus 1, alpha 2 minus 1, alpha s minus 1 is equal to 0 if s is bigger than r, and it's the product of the integral wj, alpha j, s equals to r, and it's equal to whatever if s is less than r. And this is some sort of nilpotence or unipotence property of iterated integrals. It's a nice property. It's also a limitation on how much of elements of pi 1 can be detected by iterated integrals. They can't always detect everything in pi 1. They can separate elements for the fundamental group of, say, p1 minus 0, 1, and infinity. Okay, so what we have is we have this diagram. So let's look at ln of h0 of the iterated integrals on, say, pxx m. This maps into Hom. So h0 means these are the iterated integrals whose value on a path or on a loop only depends on the homotopy class of the loop, right? So these are the homotopy functionals, or if you like, they're the locally constant functions on the loop space. The path, the connected components of this are just exactly pi 1, right? Because the two loops are in the same path component if and only if they're homotopic. So this gives you a map from, say, z pi 1 mx into c. But the nilpotence property says that if you're looking at things of length less than n, they vanish on the n plus first power of the augmentation ideal. This includes into H0 of and this goes into what you could call the continuous homomorphisms from Z pi 1 of mx into C. And the topology on the group algebra, so I didn't write down the group algebra again. Maybe I'll say a little word there. Z pi, if pi is a group, or R pi, it's just the free R module generated by pi. There's a homomorphism. So elements of this are just things of the form, say, A, G, G. And there's an augmentation that takes this to sum of the coefficients. This is some finite formal linear combination of elements of the group. The kernel is called the augmentation ideal, denoted by J. J to the S is spanned by things like this. Right? So we've got this. This includes into here. And the de Rham theorem, so these horizontal maps are given by integration, and the de Rham theorem, Chen says 1 and 2 are isos. And it also says, and then once you know that, it's trivial to say this is a Hopf algebra. So these are all the properties of a Hopf algebra. They have an augmentation, product, coproduct, and antipode. So this is a Hopf algebra. And this is a Hopf algebra where basically the structure here is the augmentation's evaluation at the identity. Product is dual to the diagonal map. Coproduct is dual to multiplication. And antipode is given by inverse. And so this is a Hopf algebra isomorphism. So 2 is a Hopf alg isom. It's just a fancy way to say that the natural operations here correspond to the natural operations over here. All right? So I'm not going to prove this in general. Again, I've got in the Bowden algebraic geometry proceedings, I give a pretty straightforward proof of this. It doesn't give all the information you need if you do this stuff in a serious way, but it's good enough for many purposes. Here I'm going to give a proof in a very special case, which is even easier. So proof for M equals P1C minus some finite set, which I'll write as A1, AN, and infinity. So this is, I'll call this set here S. Right? And just because I like calling an open subset of P1U, I'll call it U instead of M. To me, M's a C infinity manifold, and we're now entering the algebraic situation. Later on, this will just be 0, 1, and infinity, but we might as well do this because, for example, in many of Goncharov's papers, he removes the roots of unity and infinity, and I can't remember whether he removes 0 or not, but okay, 0 and the nth roots of unity and infinity. So this is a sort of nice generality for this sort of venue. So the proof is going to be remarkably easy because the fundamental group of this is free. And so that's going to make the proof almost a triviality. There's a little trick here that, or it's a useful tool. So the first thing is we're going to So let's look at this. So I'm a topologist. So this is a picture of U for me, right? So this is A1, A2, and so on, AN. And now, what's the homology? The H1 is just generated by a loop around each of the cusps here. We ignore it. Infinity's out here. It's the rectangle. And so H1 of U is equal to Z times, say, C1 plus Z times Cn, where this is, say, C2 right here, this curve. And so what's the cohomology? It's very easy to see. There are 100 ways to see this, is that H1 of U is equal to H0, writing it in a fancy way. So these are going to be forms that are holomorphic. They're rational forms on P1, holomorphic away from S, and on S they have only log poles. I wrote it like that because it's the standard terminology, but this is none other than, it's just the set of df over f, where f is a rational function on P1 and hollow on, I should say, an invertible rational function, holomorphic on U, right? So, and it's just has basis, it's just the direct sum of C times omega j, where omega j is just dz over z minus aj. So it's just, if I integrate over Cj, I integrate omega k, I just get 2 pi I times delta jk. Right? So I'm going to, so here H1 is naturally identified with some very special algebraic differential forms. And I'm going to set C, so this is just fancy, this is just notation. This is going to be the iterated integrals. It's just equal to the iterated integrals on U formed from just these forms, omega 1 up to omega n. Right? I'm only using these algebraic forms. So I'm taking, this is a subset of the standard iterated integrals. So, emphasize, I'm using only these guys. There are a lot more differential forms I could use, but I'm restricting to these. And in fact, I remarked last time that if you're on a Riemann surface and every form you're taking is holomorphic, then the iterated integral you get is automatically a homotopy functional. So this is equal to H0 because everything here is holomorphic, so everything's and we're in complex dimension 1, so everything's a homotopy functional. And so we have a map from CH omega 1 P1 log S, just these algebraic iterated integrals. And so these algebraic iterated integrals are very important, especially when S is, say, defined over a number field, or, 0, 1, and infinity. And these guys are basically motivic. So this is going to map into Hom continuous of, say, z pi 1 ux for some base point into the complex numbers. Right? Now this is, I want to stress, this is a subset of all the iterated integrals that are homotopy functional. So this is smaller than the usual doodad, right? And by definition, I should point out this is always injective because we view iterated integrals as functions on the path space. So anything that was in the kernel here would be trivial on every component of the loop space and therefore would be trivial. Anyway, that's just a remark. So this is automatic. And the what I'll prove for you is theorem. This is a Hopf-Alge isomorphism. So the Hopf algebra part's automatic because the properties of iterated integrals are automatically, the product, co-product, diagonal, and so on. Sorry, the antipode are all defined to be just dual to the operations here. So now, sorry?
You're taking few differential forms, so how can you get an isomorphism?
Yeah, that's why I wanted to stress that these things are functions on the loop space, right? Two things are equal if they have equal value. See, let me give you an example.
Exactly.
let me write something. Suppose I write integral df, right, and I evaluate it on a loop. So what is this as an iterated integral? Well, if I evaluate it on a loop, it's it's f of gamma of 1 minus f of gamma of 0. So it's just equal to 0 because gamma 1 is equal to gamma 0, right? So this iterated integral is 0, although it doesn't look 0 as a formal symbol. But I'm saying here that every...
What you're telling me is that that's injective.
Well, it's injective just because I defined iterated integrals to be not formal symbols, but functions on the path space.
Yeah. But what about being inserted?
I'm about to prove it's surjective.
Oh,
Okay, sorry.
Actually, there's a minor confusion. You defined the functions on path space. Now, is it being 0 on path space the same as 0?
Yeah, good question. Okay, so yeah, let me point this out. So I'm claiming that something's if I have a connected manifold, something's a homotopy functional on the loop space only if it is on the whole path space. Why? Because suppose I had two paths here where an iterated integral took different values on these two. And suppose I have my x's here, I can connect them up here and I can go up, around here, back here, and down here. It's very easy to see that something's a homotopy functional on the loop space at x if and only if it's a homotopy functional on all of...
That's true. I was asking even a more basic. Is it 0 on all paths if and only if it's 0 on some fixed set of loops?
Well, yeah, okay, if it's trivial on the loop space here, it's going to be...
Trivial on all paths?
Yeah. There's a change of base point formula in the notes. We'll worry about that later. Okay, but anyway, you'll see what happens here. I mean, I think things will become more obvious when we do this. Okay, so what's the trick? Yeah. Sorry? Yes? Well, that's what I'm saying here. Because we're only using these... Sorry? There's an equality here. So I could just as well, if you like, I'll put an H0 here. Is that better? But I want to stress that every one of these guys that I'm looking at is closed or is a homotopy functional. Okay, so let's write this down. So here's the trick. I'm going to let A be equal to C x1 xn. So these are indeterminates. And first of all, if I put a single diamond bracket, that means this is the free associative algebra generated by these, right? And if I put 2, I mean power series. So these are power series in the non-commuting formal variables x1 up to xn. And now I'm going to take t, and I'm going to write, this is going to be 1 plus integral w1 x1 plus integral, plus, let me just write the general term. It's so hard to write this. So the general term is going to be integral wj1 wjr xj1 xjr plus and so on. So you can think of these monomials as just a device, a combinatorial device for keeping track of which iterated integral you're using, right? So it would start out integral w1 x1 plus integral w2 x2 plus and so on. Then you get things like integral w1 w2 x1 x2 plus and so on, right? And you should view it as a function from the path space on U into A. So it's an A-valued iterated integral. This is why I've been mumbling about iterated integrals with values in an associative algebra. And if you if you think about the way power series multiply, and you think about the way iterated integrals behave on a product of paths, you will see that if I take, well, let's define theta of alpha. So alpha is an element of the loop space. So I'm going to define this to be t evaluated on alpha. Just means evaluate every coefficient on alpha. And the properties of iterated integrals simply say that theta of alpha beta is equal to theta alpha theta beta. Right? So this follows from the coproduct formula. And now, in this case, because every coefficient is a homotopy functional, T is a homotopy functional. I should stress these omega j's are precisely, remember here, omega j is equal to dz divided by z minus aj. These are these holomorphic guys. So this is a homotopy functional. So it induces a map from pi 1 of u x into A. In fact, it lands in the group of units of A because everything starts off with 1 and then everything else is in the maximal ideal generated by these guys. And in fact, it extends to, say, C, the complex group ring, just by linearity. So it's going to be an algebra map. And in fact, it is continuous, meaning, so I'll still call this theta. So if I take theta of, say, some gamma minus 1, it's going to be t minus 1 evaluated on, it's going to be t of gamma minus 1, right? But when I subtract 1 from here, I'm lying in the maximal ideal. So this is going to be an element of the ideal x1, xn, and I'm going to call this ideal I, right? So this guy is an augmented algebra. The augmentation is just simply take the constant term, right? And so this says that J here maps into I here, and because this is complete in the iadic topology, this extends to, well, this is continuous, and it extends to the J-adic completion. So theorem, it's really just a proposition, is that theta takes C pi 1 u x hat into A is an isomorphism. And it's actually, both of these guys are what are called complete Hopf algebras, and I'm not going to define them because I don't want to introduce too much formal stuff, but it's a complete Hopf algebra isomorphism. So what's the proof? So the proof, if I do it right, should only take about 5 lines. And let me just say some general things. A lot of this stuff is sort of general nonsense. In this case, you can do it all with just universal mapping properties. Let me explain why. Pi 1 of u is a free group. Now you would expect, if there's any justice in this world, that this is the free gadget here generated by the same set. But this is the free gadget generated by the same set. And in fact, you can just check on j mod j squared going to I mod I squared, that's an isomorphism. And that's basically the gadget on which everything's free. So this is an isomorphism. But that's not the proof I'm giving. This is easy because everything's free. But anyway, what I showed yesterday is that C pi 1 ux is a quotient. Well, there's a map here from the tensor algebra on H1 of u completed, and this surjects here, right? So this is j mod j squared is isomorphic to H1 of u, and in fact, H1 of u is equal to, say, equal to C times C1 plus C times Cj, and what you can just simply do is just lift these Cj's up here, and you take Cj and you just lift it up here to, say, some gamma j minus 1, where gamma j would be Here's AJ, here's our base point X. We had our loop CJ here. Just join this up to the base point anyway. Just come up, go around, and go back. And that will give me a map from H1 of U into here. It will extend to a map from the tensor algebra into here. And for just silly reasons, this is surjective. In fact, I claim it's an isomorphism. All right, so we have a diagram, tensor algebra on H1 of U. So yeah, I should make this remark. So if you read Chen's papers, he'll always say choose a basis, say here, of the first homology. So you can think of this as being a basis for the first homology, dual to the basis, omega 1, omega j. So this guy here surjects onto C pi 1 U x hat. This maps via theta into A. And then we have this composite here. So let's give this a name phi. So if I proved, so both of these guys are abstractly isomorphic because this is the tensor algebra. This is free on C1, Cn. This is free on X1, Xn. They're both the free complete, whoops, I should put a completion here, Xn. And if I just show you that this map modulo the square of the maximal ideal takes Cj to Xj, then that implies this is an isomorphism. This is an isomorphism. This can't have a kernel. And both of these maps have got to be isomorphisms. So let's see what happens here. So mod squares of maximal ideals, what happens here is Cj goes to gamma j minus 1. Right? So we're working, so the augmentation ideal happens to be called j, but that's okay. And now this goes over here. Well, gamma j goes to 1 plus the sum of the integral of wj or wk over c gamma j times xk mod, and now we've got to subtract 1, and this is mod I squared. But if I gamma j, this quantity here is just going to be 2 pi I times delta jk. So this here, all I get is just 2 pi I times xj. So Cj is going down to 2 pi I times xj, so this map here is an isomorphism. Done. So that says that you all agree. So therefore, this guy's an isomorphism. I agree, it feels like I'm pulling a rabbit out of a hat, but believe me, this one's trivial because everything's free. Okay, so why does this imply the other result? Well, so here's the point. So this is going to imply that CH was at H0 omega 1 log S, P1 log S, goes into Hain continuous, and here I'll just put C pi 1 U x hat C. This is an isomorphism because it's basically the dual of this statement. If I take the full dual of this, I recover this guy. If I take the full dual of this, I just get the algebra A. I mean, A is dual Hain of this guy here into C, and what are the dual bases? The dual bases are integral Wj1, Wjr is dual to, the dual basis is xj1, xjr. I'll let you think about it. But I claim that that statement there trivially implies this is an isomorphism because it proves that there are enough iterated integrals to detect every element of pi 1 here. you get every continuous linear functional on here is represented by an iterated integral. To see that, you just stare at the coefficients of that power series. Sorry? Yeah, sorry, yeah. So what's the Hopf algebra structure on A? So the map from A into A tends to A is the standard one where every xj is primitive. Xj tends to 1 plus 1 tends to xj. And you can check that that corresponds to the coproduct. You can check that theta preserves this coproduct. All right, so let me... I think this is an easy proof, but you just have to sit there and stare at it for a little bit if it's not evident. Let me just make... let me talk about the de Rham theorem. For Pxym. So we also want it for the fundamental groupoid, because when we're looking at P1 minus 0, 1 and infinity, you've already seen we're going to start using tangential base points, and we're going to want, it turns out the most important de Rham theorem you can prove for P1 minus 0, 1 and infinity is for paths that leave 0 with this tangent vector 0, 1 and arrive at 1 with tangent vector minus 1, 0. Right? And the most basic path is this one here, and when you take the normalized value of, in fact, this very map theta we had on this path, you get the Drinfeld associator. Right? So this is why we want a de Rham theorem for this guy. It's not just some idle generalization. So let's suppose, so now let's back to the general case. We've got Pxym. So we can think of it like this. Here's x, here's y. And now the paths from x to y, or the homotopy classes of paths, is a principal homogeneous space over the loops at this end. Right? Because if I take two paths from here to here, they differ by this loop. And likewise, they're a principal homogeneous space on the other side by the pi 1 on the other side, principal homogeneous space. And so what this says, if you look at this, if you look at H0 of Pxy, that's just the of m, with any coefficients, this is just, say, coefficients r. This is equal to the free R module on the homotopy class of paths from x to y and m. So this is equal to a free H0 Pxx m R module of rank 1. And it's also a free H0 Pyy m R module of rank 1. So remember, this guy here is just R pi 1 mx, and this guy here is R pi 1 my. So why am I doing this? Well, in order to get a de Rham theorem, I had to complete these guys here. I had to put a J-adic topology on and complete. And I want to tell you how to put a topology on this and complete. And so what we do is you just simply use, if you choose any particular path from x to y, that gives you an isomorphism of this guy with the group, with this group algebra here, right? This has a topology. So you can take the fifth power of the augmentation ideal here and just think of it as the fifth part of a filtration on H0 of this. Likewise, you could do it on the other side. Alternatively, you could do it on the other side. You get exactly the same filtration, right? So this leads you to a filtration. Jxy, 0 contains J1xy, contains J2xy. This is not powers of an ideal. It's just a filtration. This is a filtration of H0
So could you repeat that
how it's coming up? Okay, so what I'm doing is I'm saying this guy here is a free R modulo of rank 1 over this guy. So choose an isomorphism. That amounts to choosing a path from here to here. So use that isomorphism. So if I take j to the 5th over here, I just call that j to the 5th xy over here under that isomorphism. Now, it may look like it depends on a choice, but you can easily verify it doesn't depend upon the choice of this path here. And you might say, well, it depended on me choosing one endpoint rather than the other one, but you can easily check that it doesn't. It's just a trivial calculation. I just need to explain how I got the topology here. So this leads me to a completion, H0Pxy, M, R, and I can complete it in this topology.
Excuse me. So isn't it just the filtration on the module induced by the filtration on the ring?
Yeah, it's probably that. I'm not a good algebraist. Right, so you're probably all sitting there wondering why I'm saying that. Okay, so Mignon says it's the filtration on the module induced by the filtration on the...
The point is that the invertible element
Yes.
does not lie inside the ideal, the first ideal.
Okay.
Which implies that any automorphism
Yeah. Yeah, I mean, I should have said it, the way I say it in the notes is better. Jxyn of H0Pxy is equal to J x to the n of H0Pxy, etc. I mean, because the fundamental... So that's a better way. So you all understand. All right, so, but what's the de Rham theorem? And it's easily deduced from the other, just simply because everything's isomorphic, is that we have the de Rham theorem here. Simply says that you look at H0 of this maps into Hain continuous in this j-adic topology on H0 P X Y M into C, and this guy here is an isomorphism, and also that's version 1, and I'll give you version 2, which says that if you look at theta xy, which takes H0 Pxy, so this is for u equal to P1 minus S, as above, into A. This is this algebra, this guy here. And you just define it the same way. Gamma goes to T evaluated on gamma, that this guy is an isomorphism. That's also easily proved. Okay? So these are basically, the way I've stated this is much more general, but in the case of U equals P, an open subset of P1, these two statements are equivalent. And they're dual to each other. Okay, so that's enough de Rham theory. So we really want to do something with this. And a whole bunch of it, looks like a whole bunch of us prepared stuff on multiple zeta numbers and so on. So I'm no exception. So let me spend my remaining 10 minutes, where's Layla? Yes, 10 minutes, on so it looks like there's 4 different conventions that one can use here. So I just want to lay out the conventions I'm using. So we've seen that zeta n1 and R is equal to the sum k1 less than, so 0 less than k1 less than k2 less than kr of 1 divided by k1 to the n1 kr to the nr. And I think we need nr to be greater than or equal to 2 for this guy to converge. So this is a multiple zeta number. And in fact, since I've only got 10 minutes, I think I will say a few short things here, I do discuss the product, the Stuffle product on these. I call it the percolant here. I just made that name up. I like Stuffle better. But I'm going to skip over that. I'm going to just go to the representation by iterated integrals and make some remarks because they're relevant to something that Layla said yesterday. I'll just talk about how the antipode plays a role here. Okay, so there's the integral representation, which is due to Kontsevich. And so this is equal to, you can check, it's the integral from 0 to 1 of omega 1, and again, Layla stated this, but let me, again, because of differences of conventions and notation, let me state it. Okay, so there are several issues here. Omega 1 has a pole at 1, and omega 0 has a pole at 0. You can easily check, so maybe I should really define this as to be the limit of the integral from epsilon to 1 minus epsilon of this thing, and remark that it converges precisely when, such iterated integrals converge precisely when you have an omega 1 first and an omega 0 last. Makes sense because omega 0 is regular at 1 and omega 1 is regular at 0. Yeah. Omega 0, yeah, sorry. Here we are at, we're on P1 minus 0, 1, and infinity. Omega 0 is equal to dz over z, and omega 1 is equal to dz over 1 minus z. So that's indifferent by a sign from what I just did in the previous example. But the remark, and again, you can multiply these using the shuffle product formula and get the shuffle product. And I got some examples worked out there. And you can play the shuffle product off against the Stuffle product and get the so-called double shuffle relations. But let me concentrate on one further example. So let me just show you the relevance of the antipode because it came up. Okay, so maybe I'll call it the antipode relation. And again, this is a question of whether this relation would follow from, say, the shuffle and Stuffle relations. Yes? Okay, it's done. But let me write down the antipode relation anyway. Okay, so what we'll do is let's look at the automorphism f goes to 1 minus z. This automorphism so f here takes p1 minus 0, 1, and infinity into itself. And notice that we've got the path 0, 1. What happens if we compose it with f? It's the path 1, 0. So for me, the path AB means the linear path from A to B. Right, so this is the path from 0 to 1. It's the path from 1 to 0. And you can also check that f star of omega j, of omega 1 equals minus omega 0. F star of omega 0 equals minus omega 1. And so let's look at, so let's let the weight be n1 plus nr. So we'll look at zeta n1 nr. So we've seen this is the integral from 0 to 1 of omega 1, omega 0, blah, blah, blah. So n1 of these down to omega 1, omega 0. Okay? There's just exactly 1 omega 1 in each block. Now we can write this as minus 1 to the omega times the integral from 0 to 1 of f star omega 1, f star omega 0 f star omega 0. So all I did is, whoops, 0, 1. Okay, I just used this relation here that f star swaps omega 1 and omega 0. And maybe slightly better, instead of writing integral 0 to 1, I'll write it integral from 0 to, think of it over this path. And now I'm going to apply the naturality formula. So that says this would be equal to minus 1 to the omega integral from of f star 0, 1. And now it's going to be omega 0, omega 1, omega 1, and 1, down to omega 0, omega 1, omega 1, and r, right? But now this path here is really the path 1, 0, which is also equal to the path 0, 1 inverse. So I want to turn it back into this path, so I now apply the antipode, which says reverse the order of all of these and multiply by minus 1 to the length. Well, the length is omega, so when I apply, so this is going to be antipode. And I'm going to get the integral from 0 to 1 of omega 1, omega 1, omega 0, right, nr down to omega 1, omega 1, omega 0, and this will be n1, right? And that's again a multiple zeta number. It's a convergent iterated integral. It starts with omega 1, ends with omega 0. And now let me give you an example. So the example is, you can easily check that zeta of m1 plus 1, mr plus 1 is equal to zeta of 1, 1, 2, and there'll be, say, mr of these, 1, 1, you just get blocks, 1, 1, 2, mr minus 1 down to 1, m1. Right, so that's, and I guess I'm going to finish 1 minute early.